Okay. Okay, so we can start. So, well, welcome everyone to this session of the virtual seminar on geometry with symmetries. So it's a pleasure to have Jaime Santos Rodríguez from the Universidad Autónoma de Madrid, who will talk about symmetries of Wasserstein spaces. So welcome, Jaime. Thanks for giving a talk. And thank you everyone for
Okay. First of all, I would like to thank the organizers for letting me speak today. And as Fernando just told everyone, I will be speaking about symmetries of Wasserstein spaces. Well, the thing is that using the Monge-Kantorovich optimal transport problem, we can put a metric on the space of probability measures such that with this new metric space, you can do many things. For example, it has been very useful to give an adequate notion of lower Ricci curvature bounds for non-smooth spaces. But the thing is that this space, the Wasserstein space, will also share many geometrical properties with the base space X. And the plan for today is going to be the following. First, I will talk about the optimal transport problem, define it rigorously, and give some examples of it. Then I will define the Wasserstein spaces and talk about some of their geometric properties. And finally, I will focus on isometries, on things that are known, as well as some contributions, and some things that one can try for further research. So let's begin with the optimal transport problem. Assume we have this setting. You have in red a pile of sand, and you have on the right some hole. And these are modeled by probability measures mu and nu. And the thing now is you want to send all of the sand to the hole in order to fill it. And how you do that? Okay, you take point X in the support of mu, and you assign it a destination Y. So you send all the sand there to Y to fill it. And you repeat it for every point X in the support. You pick another point X prime and you send it to another location. However, you can also do something like this. You take X, you notice, okay, there's too much sand in there. And you take part of it to Y and the rest to Z. And again, you repeat this for every point X in the support of mu. And the thing is that in the end, you end up having all of these way to send mass from one point to another, described by pairs of points, X and Y, where X is where we're taking the sand and Y is where it's being taken to. And this will be now a probability measure pi, but defined in the product of our space with itself. And once we have this, we would like to find the best way to do this. That is, we would like to find the best way to send all of the sand from mu to nu. And this is basically the optimal transport problem. Now, in a more rigorous way, we have the following setting. We have XD, a complete and separable metric space, and some exponent P greater or equal than 1. And we have two probability measures, mu and nu, such that we would like to minimize the following function. You take a measure pi, and you take the integral of the p power of the distance with respect to that pi. And the pi will be a measure which is going to be called an admissible plan. That is, it will be a measure pi in the product space, such that if we take the first marginal, we recover the measure mu. And if we take the second marginal, we recover the measure nu. Again, this is just formalizing the thing I described in the drawings in the last couple of slides. And well, we can observe the following two things. First of all, we will always have at least one admissible plan, which is just the product measure. We take the product of mu with nu, and that's going to satisfy the condition. And the second and most important is that solutions to this problem always exist. That is, I can always find a minimizer. The idea behind the proof is that the set of admissible plans is going to be compact with respect to the narrow topology. And it's easy to see that this set is going to be convex. So you can take convex combinations of these admissible plans, and they will again be admissible plans. And finally, as we can see, this functional is linear. So we can always find optimal transports. But let me give an example of these admissible plans in the Euclidean setting. Consider the measures mu, which is going to be the Lebesgue measure in the unit interval, and nu, the Lebesgue measure, but in the shifted interval in 1, 2. And the thing is that, as previously mentioned, one can take as an admissible plan the product measure. Okay, fine. But you can find many others. For example, consider the maps T and S given by T of X will be just shifting all my points 1, which is X plus 1, and S of X, which is going to be 2 minus X. Then if I define these new measures via push forwards, the identity comma T of mu and the identity comma S of mu, I will again have admissible plans. So I can have at least 3 and the convex combinations of them. And the funny thing is that you can in fact prove that for the map T, okay, so I have solutions to this problem, and how can I use them? Well, I can use them, for example, to define the Wasserstein space. Again, I have XD, a complete and separable metric space with some exponent p greater or equal than 1. And I won't take all of the probability measures, but I will restrict myself to those that have finite p moments. That is, I will look at probability measures such that if you fix a point x0 and you take the integral of the p power from that point x0, I get that the integral with respect to mu is finite. And once I have this set, I can give a distance on it using the solutions to the Monge-Kantorovich problem. And the result will be called the LP Wasserstein space. The definition is just you take 2 measures, mu and nu, of finite p moments, and you looked at the solutions to the Monge-Kantorovich problem. That is, I look at the infimum of the minimum of the integral of the distance to the p power with respect to pi, where pi is an admissible plan. So I know that I will always find one that minimizes it, so there will always exist at least one pi that realizes this integral. So, and this will give us a distance between probability measures. This distance will have many nice properties. I will just enlist a couple of them. First of all, my space with this metric will always be complete and separable. The Wasserstein space will be compact if and only if the base space is compact. If, however, my space X is not bounded, then the space of probability measures will not be locally compact. Thirdly, and this will be important later, that if I take the map that sends each point to the corresponding Dirac delta, then this defines an isometric embedding of X into Wasserstein space. So in the space of probability measures, I have a copy of my base space of X such that the distances are preserved. And the last feature that is perhaps the most geometric one is that if I take the exponent to be p equal 2, then x has non-negative sectional curvature if and only if the Wasserstein space has non-negatively sectional curvature in the sense of Alexandrov. That is, in the sense of these comparison triangles. Another nice thing that will really help us when we talk about geodesics, isometries, sorry, is that the Wasserstein space is going to be a geodesic space. Here, I will like to point out something that I will call curves, gamma, from the unit interval 0, 1 to x geodesics, if the distance between gamma at s to gamma at t equals the absolute value of the difference between s and t times the distance between the endpoints, gamma 0 and gamma 1. That is for all s and t. So I will always consider geodesics to be distance minimizing. I will denote the space of geodesics of x by g of x. And I will say that the space is geodesic if for any 2 points, I can always find a curve that is a geodesic in this sense. And the thing is that if my base space is geodesic, say it's a Riemannian manifold, then the Wasserstein space will also be a geodesic space. And we can actually describe the geodesics in the Wasserstein space in a very nice way. To do so, I will require an auxiliary map for every parameter t between 0 and 1. We just consider the evaluation maps E sub t between the space of probability measure, the space of geodesics and x. Just you take a curve and you evaluate it at time t. And the first result of today is going to be that if x is a geodesic space, then the Wasserstein space is also geodesic. And the following are equivalent. A curve in the Wasserstein space is a geodesic if and only if there exists another measure, eta, which is now going to be supported on the probability on the geodesics, such that when I take the push forward with the endpoints, I recover an optimal transport, and the curve eta of t is just pushing forward eta with the evaluation maps. So intuitively, this is just telling us that geodesics in the Wasserstein space look like if we're moving mass from one measure to another by taking geodesics. I just move all the mass by choosing one geodesic with some geodesics, and until I get to the endpoint. But I think this is better if I just give explicit examples. So take 2 points P and Q in X, then it is easily seen that there's going to be only one admissible plan, the product measure with delta P and times delta Q. And the thing is that I can do the following. If I take a geodesic gamma, say joining P and Q, then in this drawing on the left, the geodesic in the Wasserstein space will be just moving along Dirac deltas supported along the geodesic. That is, the geodesic is just delta gamma sub t. Okay, so this is very intuitive, but say I have a different geodesic sigma joining P with Q. Then I can do what's drawn on the right. I can take a convex combination of the delta at gamma sub t plus the delta at sigma sub t. So this looks like I have my two Dirac masses, delta sub p and delta q, and I split the mass and I take, say, 1/2 along gamma and the other half along sigma. So the mass is moving along geodesics, but even in this very simple case of just taking Dirac deltas, there might be some more complicated behavior than just taking the mass along one geodesic. So I can have more freedom and split the mass between them. So that's with respect to geodesics. Now, once I have all of these nice features, I can, well, go on to isometries of these spaces, since they're a metric space on their own. Maybe we can talk about that. So again, I can take P greater or equal than 1 and define the Wasserstein, LP Wasserstein distance on measures with finite P moments. And something that's quite natural is that if isof of X is the isometry group of X, I can give an action on the probability space of probability measures via push forwards. I can take an isometry G and measure mu, and I just send it to G push forward mu. And the thing is that this will define an action by isometries on the Wasserstein space. So the natural question, or at least what one thinks, is that, okay, my Wasserstein space is itself a metric space. It has its symmetries. Are these two groups equal? More precisely, I would like to know if, given any isometry phi in the Wasserstein space, if there exists a corresponding G in the isometry group of X, such that the action looks just like phi at mu, is just pushing forward mu with this particular G for all measures mu in the Wasserstein space. So this is a very natural question. And such, before I even thought about it, someone else has already considered it, at least on Euclidean spaces. And in 2010, Lebner found something quite surprising, that there are isometries of the L2 Wasserstein space in Rn that don't come from isometries of Rn. What he finds is actually something like this, that there exist isometries phi in the isometry group of the Wasserstein space, that they are not the identity, but such that they fix every Dirac delta. So remember that I've embedded my space X by taking each point to its Dirac delta. So what it's saying is that that embedded image is just fixed, but somehow there are isometries that move other measures. And what's even more surprising is that if you take the line, then there are some isometries that actually do some quite surprising things. That is, they pull away mass to infinity. And this is what I want to describe now. What do I mean by pulling mass away to infinity? And to do so, I will need to introduce two technical results from Klugner. The first one is that if I take n greater or equal than 2, I can define the set delta sub n to be projective measures that look like convex combinations of Dirac deltas. Say for n equals to 2, you take a convex combination of at most 2 atoms. And the thing is that if you're in R, then when you take the convex hull of those that have at most n atoms, you get the next one. You get the one that is supported on at most n plus 1 atoms. Why is this useful? Because if I want to define an isometry, I can just define it for n equals 2 and then extend it by taking the convex hull. And the thing is that these measures that have atoms, a finite number of atoms, when you make n go towards infinity, they will be a dense set. So you can have it defined for every probability measure. So the strategy is that one. I can just look at n equals to 2, define the isometry for measures that have 2 atoms, and then extend. And the next thing is that if you take an element, mu, that is supported on 2 atoms, then we can describe it in a more convenient way, just by looking at some parameters. So mu is going to depend really on 3 things, on x, on sigma, and on p. P is going to be some parameter in R. X is going to be the barycenter or the center of mass of mu. And sigma is just going to be the distance to the barycenter. And with these 3 things, you can actually write the measure mu in the following way. You take the exponential to minus p over the exponential at p to p plus the exponential to minus p. So that's one weight. And you have the delta at x minus sigma, the exponential at p, plus something similar, the same weight, except that it has the exponential to the p, and the other weight is x plus the exponential. So why do I want this expression for measures at 2 atoms? Because then you can define a map in this way. Pick any t in R, that's going to be fixed, and then you define a map phi from measures with 2 atoms to measures with 2 atoms in the following way. You take mu with this data x, sigma, and p, and you send it to mu with x, sigma, and p plus t. So we are preserving the barycenters and the distance to the barycenter, but we are changing the weights in p. So here the p's here will just be p plus t or whatever. So you are changing the amount of mass that it's given to each atom. And notice that each Dirac delta also has some dependence on p. So you're moving those atoms as well. Once more, notice that if you have just one atom, then that is, if sigma is just 0, then the measure is fixed for all x in R. And this image in the bottom is just describing what we're doing for, say, t positive. So you take in blue one measure, x is going to be the barycenter, and you apply the isometry. And what's going to do is that it's going to take, say, the atom on the left further away from x, while the other atom is going to get closer to x in order to compensate and make sure that you're still at distance sigma from the barycenter. And the thing is that you can keep applying this isometry, and then you notice that the atom on the right is going to converge to x, but the other one, the one on the left, is just going to go towards infinity. So that's what I mean by taking mass towards infinity. So that's something that's new and that's quite surprising. But one thing that one can also wonder is that, okay, I defined the Wasserstein distance for all exponents greater or equal than 1. So let's take p equals 1 and see what happens, because then maybe I can say something else. I will have then the L1 Wasserstein space. But there are some things that are weird that can happen. The first one is that geodesics in the L1 Wasserstein distance can be different. For example, if you take any 2 points, x and y, then the curve that is just taking the convex combinations of the Dirac deltas, that sends t to 1 minus t times the Dirac delta at x plus t, the Dirac delta at y, is going to be a geodesic between delta x and delta y. This is something that never happens for p strictly greater than 1. For p equals 2, it never happens. It always happens in this one. And notice that this curve does not correspond to moving along geodesics in my base space. So this is something a bit different. And the thing is that maybe with this weird behavior, one can expect some exotic isometries to appear. Where exotic, I mean something like this one here, where you have this weird behavior that you're fixing Dirac deltas, but you're still having something move. And well, this was first, there are two things that are known of. The first one's a theorem by Geher, Titkos, and Birostek, where they prove that there's an isometry J for the Wasserstein, L1 Wasserstein space of the interval, of the closed interval, that splits mass. More precisely, that sends Dirac deltas to measures supported in 2 points. That is, I take a J of delta t, and it just sends 1 minus t mass to delta 0 and t mass to delta 1. So it takes a measure with 1 atom and sends it to something that has 2. And this is sort of to be expected from having that this curve is a geodesic. So if you think about it, an isometry must send geodesics to geodesics. So it's just telling us that, okay, the geodesic from that just moving along Dirac deltas, I just send it to this new one. And this is exactly the case. But the funny thing is that if you look instead at not on the closed interval, but the whole R, the whole line, then the isometry groups of R and of the L1 Wasserstein space do coincide. So this is something that's very curious, that even if you still have geodesics that do split mass, that move not along geodesics, but along other curves in Wasserstein space, sometimes you cannot expect geodesic, these exotic isometries to appear. So this was known in the literature. So what one does, or at least what I came up with, is that maybe one can study compact spaces, and then maybe one can expect rigidity, but you take p strictly greater than 1. Maybe then you cannot have this mass going towards infinity, obviously. And if you take p strictly greater than 1, then you have a bit more control about how geodesics look in the Wasserstein space. Okay, this is the setting. And the first thing that one notices is that if I take a map F from X to itself, and I take the push forward with F of a Dirac delta, then I always get a Dirac delta. That is, the push forward of delta of X is going to be the delta at F of X. So if I want to look at if there's the possibility of some exotic isometries, first I will need to look at how these isometries move the embedded image of X. So that's the first thing I want to know, that if my isometry already splits the mass, it sends a Dirac delta to something with more atoms, then of course it's going to be exotic. And this problem is there's going to be more isometries, but if it doesn't, then okay, maybe one can still need to work a bit more, but at least you have something. And well, the first result is that if I have XD compact, M is going to be a measure on X. I will assume that geodesics do not branch, with M satisfying some technical requirements that I will not really define. For some P strictly greater than 1, then any isometry leaves the set of Dirac deltas invariant. That is, phi always sends one Dirac delta to another Dirac delta. Okay, this is perhaps a bit too abstract, but just to set things, there are two settings where this is true. First, for p equals to 2, then you have this for non-branching RCD spaces, that is, spaces that have a lower reach curvature bound that are quite popular right now. The second one is that if you have p strictly greater than 1, and you equip a Riemannian manifold with a locally doubling measure, just take the volume, then they will satisfy the hypothesis of the theorem. So I will not delve into what it means qualitatively non-degenerate or the good transport, but instead I will like to present the proof of this for Riemannian manifolds. And in order to do so, I will need two technical results that will help me prove this. And that they have to do with the conditions I'm asking. So the first one is that if I take XDM as before, or just consider a Riemannian manifold, and if you take as an initial measure mu0, one that is absolutely continuous with respect to M, just with volume, and any other measure mu1, then there exists a unique geodesic joining them. And if you move along this geodesic, for mu of t will still be absolutely continuous for all time until perhaps the very end, because I took mu1 to be just some arbitrary measure. So I will move along absolutely continuous measures. The second thing I will need is a property of convexity of the distance function, which is the following. Take, say, a Riemann manifold, and mu an absolutely continuous measure. Then the function that is a p power of the distance from mu is strictly convex in the following sense. If I take any two measures, nu0 and nu1, and some t between 0 and 1, then the p power of the distance from mu of the convex combination of these two measures is strictly less 1 minus t times the p power of the distance from mu to nu0 plus t to the p power of mu to nu1. Here I would like to emphasize that here I'm considering that the p in both of these propositions is strictly greater than 1. If one takes p equal to 1, then both of these are false. Actually, they are false even in R. So I really need p to be strictly greater than 1. But with these two things, I can prove the result, and that's what I'm going to do now. So the sketch of the proof, not all the details, but the thing is that, say, take phi, an isometry of the LP Wasserstein space of some Riemannian manifold, compact Riemannian manifold, and you look at some measure mu, absolutely continuous with respect to volume, such that phi of -1 of mu is not mu. It doesn't fix mu. We can always assume that we can find at least one of these. Otherwise, phi would be forced to be the identity, so there's nothing to prove there. But once we have them, we can do the following. Okay, take the geodesic between mu and phi of inverse of phi of mu. So it just looks sort of like this. There's a unique one, and from the first proposition. From the second one, if I take an interior measure, that is, if I move along this geodesic, say at nu, I will still be absolutely continuous. So that's great. And once I have this, okay, since I'm dealing with an isometry, then the image of a geodesic is going to be again a geodesic, which is going to look like in the picture. It now goes from phi of mu to mu, and it passes through phi of nu. And this works because the geodesic is unique, and I have the other property that these measures remain absolutely continuous. So what I find here is that there exist measures that remain absolutely continuous under isometries. Okay, great. I have many of these. So I use the first proposition. So the next one is, okay, I consider now these functionals that are the p powers of the distance from nu and of phi of nu. And I know that they are extremely convex in the sense that is below in gray. That is that if I take convex combinations, then I have a strict inequality. And I remember that, okay, these are continuous functions. And as the domain is compact, I can take the maximum of them. It's going to be something finite. And I just look at the argmax of them. That is, I looked at measures that realize that maximum. And the thing that is, if you computed the definition, then you can actually see that this maximum is going to be realized on a Dirac delta. That is, if that wasn't the case, I could write my measure as a convex combination of two other probability measures, and then I can use the strict convexity to arrive at a contradiction. Okay, so I have these two sets that are contained in the set of Dirac deltas. And what I do with them? Well, I notice that if I take the argmax of the p power of the distance from nu and apply phi, then I get the argmax of the p power of the distance from phi of nu, since phi is an isometry, and this is clear. And these sets remain in the set of Dirac deltas. And all of this is just telling me that there exists a point x in M such that the Dirac delta at x under phi goes to some other Dirac delta, say at y. Okay, so I found one such Dirac delta. And here is really where one uses the fact that we are on our Riemannian manifold. Because then I just pick M, some other point in M, such that the geodesic, the unique geodesic joining it to X, can be extended a little bit up to some other point Q. And then I have some similar argument. I just take the unique geodesic in the Wasserstein space, go from delta P to delta Q, that passes through delta of X. Again, I apply the isometry. It's going to go to another geodesic. Now, one that goes from phi of delta P to phi of delta Q, and that passes through Y. And since my geodesics do not branch, it can be proved that, and this is something that applies in general for non-branching spaces, is that a Dirac delta can only appear in the interior of a geodesic if both of the endpoints are Dirac deltas. So by this, then I can conclude that both phi of delta p and phi of delta q are also Dirac deltas. And now the important thing is that since I can, since the points p that satisfy this condition of extending the geodesic to x just a little bit are dense, then I can just conclude that phi of every Dirac delta is again a Dirac delta, and I'm done. I have proved the result. For the general case, precisely the thing that makes it more complicated is that one cannot, in general, extend geodesics because one can be very unlucky with this point x that one finds, and say in Alexandrov space is just an extremal point. So there's absolutely no geodesic that can extend it. So you need to work a bit more. But then all the other assumptions that are made really help you with that in order to conclude that you actually are forced to send every Dirac delta to another Dirac delta. But fortunately, for Riemann and manifolds, the proof is much more simpler. Okay, so this theorem just tells you that you fix Dirac deltas, but this may not be enough. So for the rigidity, we needed to rely on more information on the geometry of the space. And there's two results. The first one says that if M is a closed Riemannian manifold with a strictly positive sectional curvature, then the Wasserstein phase for p equals 2 is isometrically rigid. That just means that the isometric groups of M and of the L2 Wasserstein space coincide, but one really relies on p being equal to 2 and on the positive sectional curvature. And the second one is that if M is a compact rank 1 symmetric space, that is, if it is a sphere, projective space, a quaternionic space with the symmetric distance, then I have the same for every p strictly greater than 1. That is because for these crosses, one really knows a lot of things, like, for example, that the cut locus is very well behaved and you know how geodesics look. So you can come up with other geometric arguments that really help you out, but that you don't really have for general manifolds. So let me finish just by stating some further work and things that one can consider that go from most obvious to maybe less obvious. The first one, that's like really the first thing that people ask me, is that if it is known that the isometric group of a Wasserstein space is a Lie group, which is something that always happens for manifolds. And well, even in the compact case, I don't know. And most of the proofs that I know that for checking this rely on some other structure, like having tangent spaces and looking at how the isometry acts on them. So maybe you need to come up with something else. The second one is that if maybe one can push forward these results to the case of p equal 1, and maybe one could try with the crosses, since you already have like so many geometric properties on them. So maybe that's the first place you can try. Because okay, the case of of R and Rn has already been done. So maybe next part is this one. And lastly, well, there are other distances that are motivated by optimal transport problems that one can use to give a distance on the space of probability measures. And some that appear in the literature are like the partial optimal transport, or maybe you don't want to use LP spaces, but use other Sobolev spaces like the Orlik ones. And there are many others. So maybe one can try again to replicate these things, just maybe asking that you can isometrically embed the space and you can give a natural action of the isometric group of the base space on this whole space of probability measures, and then maybe one can try things. So I don't know, these are three things that one can try. And I guess this is a good place to stop. Thank you very much.
Thank you very much, Jaime, for this very nice and interesting talk. So there is some time for questions. So maybe. So so maybe is there a question, Xingyu?
Oh, yeah, I just wanted to ask, for example, if there's a natural measure on the Wasserstein space, say just P2.
I'm not aware of it. I think I saw a paper by Sturm that came up on the archive like a couple of weeks ago, where he tries to define something that could be a natural reference measure on it. But I mean, I have not read it in detail, but even it's not clear that exists in general cases. So I think he has it for like tori, flat tori or something. But the thing is that if with this reference measure, maybe, I don't know, depends, you could maybe try to prove some lower Ricci curvature bound or something, but I'm not sure. I mean, there's that paper that tries to do something, but I'm not sure if that's like the good one, let's say.
Okay, okay. And is there any like topological results on the Wasserstein space?
Well, the thing is that the Wasserstein space is contractible. So anything about
Okay. I see.
fundamental groups or whatever is just like, but it's not really reflected. I don't know, maybe you could try to define something else that sort of like forces maybe the loops that you consider do not contract because you add something else. Maybe I'm not sure, but at least if you just take the usual, just looking at loops and trying to contract them, they will always contract regardless of the topology of your base space. So in that sense, there's not much to do.
Okay, I see. Thank you.
Well, thank you for your questions. So are there other questions? So there's a question in the chat from Lawrence Maillet. So would it be tractable to look at other closed symmetric spaces besides the crosses? Yeah. Comparing the isometries to the Wasserstein spaces.
Yes, maybe, but I mean, in the proofs, I really rely on all of the properties of the rank 1 ones, because I mean, you have like all these very useful things that you always have, like isometrically embedded another cross of lower dimensions, so you can just do an inductive argument and things like that. But yeah, maybe one can try with other symmetric spaces, for example, but maybe one would need to find like a good enough family of them and maybe have enough properties and try to exploit them as much as possible. But yeah, maybe one can try with them.
Thank you, Jaime. Thanks from Lawrence. Thank you. So maybe we have time for a few more questions. So it seems there are no other questions. So, well, let us thank Jaime again for the nice talk. Thank you, Jaime, for giving a talk in the seminar. And thank you everyone for joining, and we hope to see you in the next in the coming talks. So thank you.
Thank you for having me.